Okay, good morning, everyone. So we have one more sign convention to talk about. This time it deals with capacitors, and then we're going to investigate our last topic, which is RC circuits. So what happens when we actually put both a resistor and a capacitor into a circuit? So, so good. So this last one is capacitors. So let's say this is my positively charged plate. This is my negatively charged plate. So if I go across the capacitor from the positive side to the negative side, we're going to get a potential drop. That potential drop then is given by Q over C. So the charge on this guy, where this guy's going to have a total charge of Q divided by the capacitance. And if I go in the opposite direction from the negative side to the positive side, we have the potential increase, where that potential increase then is just Q over C. Okay. So this is our last sign convention. So we're going to use this to analyze these guys here, which are RC circuits. So we already did RC circuits in lab, but we're going to talk about how these things actually work. So let's say I have my battery. So here's my battery with some potential V. That's going to create a current thanks to our resistor, where our current then, I'm going to get I going in this direction, is then going to flow through both the resistor and then across the capacitor here. Now, since it's the positive side of the battery, this side of the capacitor is now going to become positively charged, where this side now is going to become negatively charged. So in this case, we're going to use a loop rule. So let's use the loop rule to analyze this guy. So let's start up at a point. Let's call this my point at A, and then we're going to go around the loop back to this particular point. So starting here, first thing I'm going to do is go across the battery from the negative side to the positive side. So if I go from negative to positive, is that positive or negative? Positive, good. So I'm getting my EMF, or sorry, not EMF. I called it V. So I'm going to get my battery, or my EMF in this case. Now we're going to go across the resistor in the same direction as the current. So is that positive or negative? Negative. So I'm going to get a minus I times R. And then now we're going to go across the capacitor from the positive side to the negative side. So is that positive or negative? Negative. Good. So I'm going to get a negative Q over C is equal to 0. All right. So what we want to do is find the charge on this guy as a function of time. So what we know is, as we talk about with the capacitors, these charges are going to start to build up on here, which means it's going to start off, say, with 0 amount of charge, and that charge is going to build up over time. As the charge increases over time, what we also know from lab is that if this was a light bulb, the light bulb got dimmer and dimmer and dimmer and dimmer and dimmer, which means that the current is going to get smaller, 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 and smaller. And so eventually it's going to go to 0. Now, to do that, we also have to remember that the current is equal to the time rate of change of the charge. So here, I'm going to replace this I with dq dt. So I'm going to get V then minus R times dq dt minus Q over C is then equal to 0. Or I'm going to rearrange this guy by bringing these two terms to this side to make them positive. So get all my charge terms on one side, and then actually, I don't even have to do that. Let me move simply this term. Let me do it that way. So I'm going to get a V minus Q over C is then equal to an R dq dt. So let's do it this way. Next, I'm going to separate this expression. So we're going to multiply both sides by dt over R. Okay. To get rid of that R and that dt. So in this case, we're going to get that dq is then equal to what? 1 over R times V minus Q over C. Finally, I'm going to factor out the C to put it out front. So I'm going to get a 1 over RC times VC minus Q. Everybody's okay with that? And I dropped my dt somewhere. So let's put my dt back here. There we go. Forgot my dt. Was doing okay? Actually, I multiplied by dt, didn't I? Yeah, so this dt goes away and it goes over here. There we go. That's better. I'll get my brain straight at some point. Everyone doing okay? So now, since I want to know the charge as the function of time, I'm simply going to integrate both sides of this. So I'm going to integrate this side from 0 to the total amount of charge of Q. And this side I'm going to integrate then from 0 to T. Now, one thing you'll notice is what? On this side, I have a charge term. On this side, I have a charge term. So I can't integrate this guy because I already had charge over here. And I'm trying to figure out how the charge changes on this side. So what I have to do is I have to bring this term over here, which depends on charge, to this side because I want all the charge on one side. Okay with that? So the way we're going to do that is simply going to divide both sides by this final term here. So let's do that. So now we're going to get the integral from 0 to q of dq over vc minus q is then equal to 1 over rc, which is a constant integral of dt from 0 to t. He's doing okay? Now, what's the integral of dt? T evaluate from 0 to t. T minus 0, which is the same thing as t. So I'm going to get a t over rc on this side. For this side over here, I'm going to use a u substitution. So u I'm going to call vc minus q, which means that du is the same thing as minus dq. Okay? So my left-hand side then is going to be minus integral du over u. And now I need my bounds of integration. So at q is equal to 0, this is now just simply vc. And then at q, I'm going to get a vc minus q. So my bounds of integration go from vc to vc minus q. Okay? Finally, I'm going to get rid of the negative sign over here and put it over here. Just for fun. What's the integral of 1 over u du? Natural log. So this thing is going to become the natural log of vc minus q over vc is then equal to minus t over rc. Now what I want, again, is the charge on the capacitor plates as a function of time. So now I just have to simply solve this guy for q. Okay? How do I get rid of a natural log? Exponentiate, right? So let's exponentiate both sides. So let's do that. So exponentiating, we're going to get, in this case, vc minus q is then equal to vc times e to the minus t over rc. So I did two things here. I exponentiated and I also multiplied by vc. Okay. Finally, what I want is q. So I'm going to add q to this side, subtract this term to this side. And finally, I'm going to get a vc times 1 minus e to the minus t over rc is then equal to q. So what this thing says then is what? As I am charging the capacitor, which in this case I'm charging because I have the battery, the charge on this thing is going to increase exponentially. Okay, so let's plot this thing and talk about what it looks like. So if I plot this, what is this thing going to be at t is equal to 0? So if I evaluate this at t is equal to 0, what do I get? 0, right? Which I have to, because we're assuming that the initial charge is equal to 0. So I get a e to the 0, which is simply 1, 1 minus 1, which is 0. So this thing starts off at 0. Now, from here, what happens as t goes to infinity? What am I going to get? So if t goes to infinity, what happens to the negative exponential? If t goes to infinity. Goes to 0, good, because this is the same thing as 1 over e to the t. T goes to infinity, this thing goes as 1 over infinity, which is the same thing as 0. So as t goes to infinity, this term is going to go to 0, which means I'm left with this term. Okay? So this thing then is going to reach some charge dictated then by the battery and the capacitor, which means that ultimately my charge then is going to asymptotically approach this maximum amount of charge. So this is what we're going to call Q max. So Q max then is determined by the potential in the capacitance. Okay? We'll talk a little bit further what all this actually means. Now, let's talk about the charge, or sorry, the current. So the current running through then the resistor is going to be equal then to the change in charge with respect to time. So let's take the derivative of this thing. Take the derivative of that. This first term is a constant, so that's going to go away. I'm going to get the derivative of an exponential. What's the derivative of an exponential? Exponential multiplied by what? The derivative of exactly the exponents here. So it's going to be the same thing then as what? Vc divided by Rc e to the minus t over Rc. Okay? The two c's are going to cancel. And then this thing is going to be simply what? V over R, e to the minus t over Rc. Now let's plot this guy. Talk about what this guy's going to do. So here, this is T. This is then my current. Should probably put axes on here. So this is my charge and my time. So at T is equal to 0, what is this thing? At T is equal to 0. Just V over C, right? So this thing is going to start off at V over C. All right. And then as time goes off to infinity, what do I get? Oh, sorry, V over R. So as T goes to infinity, what do I get? 0, right? So this thing is going to exponentially decay and then asymptotically approach 0, right? So this is what my current is doing as a function of time. So let's talk about this. What does this actually mean? So this means that T is equal to 0. This thing is going with maximum currents, where that maximum current is dictated by Ohm's law, which is simply V over R. So initially, at time is equal to 0, it acts as if the capacitor is not here. Okay? So it acts as if this is just a straight wire. All the current then is only dictated by the resistor. As time goes on, because the charge is building up, the current is getting smaller exponentially, while the charge on the capacitor is increasing exponentially. Okay? Until eventually what's going to happen is when this thing reaches maximum charge, it can no longer have work done on it by the battery because it has reached the maximum amount of work that it can do, which means current can no longer flow because no longer charges are moving. Okay? That's what's happening as T is going to infinity. As T goes to infinity, this thing is going to reach its maximum charge. My current has to go to 0 because I can no longer have charges flowing. Okay? Makes beautiful, perfect sense. Hopefully. Mia says no, but that's okay. We'll get there. Okay. So this is what happens when it's charging. So when it's charging, we're going to rewrite this then as the charge is equal to Q max times 1 minus e to the minus t over t, where tau is what's known as the time constant, which is simply ROC. So this is what we call the time constant. So what's the time constant? So the time constant is effectively the amount of time it reaches, or it takes for this thing to reach about 66% of its maximum charge. This is what the time constant means. So the time constant means then the time required to reach roughly 66% of its max charge. Is it going okay? And in this case, this guy then would be equal to I max times e to the minus t over tau, where it has exactly the same time constants. Right? So as far as charging is concerned, all I really want you to know is that this is the charge on it as a function of time, and then this is the current on it as a function of time. We're doing okay? Not too bad. Mm-hmm. So let's do this now for the discharging case. So let's look at discharging. So the only thing that's going to be different here is when I look at discharging, we're now going to get rid of the battery. So what's that? It's missing a what? Oh, this one, it's because it's covered by the red. Yeah, no, you're fine. Yeah, sorry, I should do that. Then the negative sign is going to be there. Yeah, so it was just covered by the red, but that's okay. So good. So what we're going to do now is we're going to take a charged capacitor and put it into a series with a resistor, where in this case, since it becomes initially charged, it doesn't want to be charged. So all the charges are going to move. So in this case, the negative charges are actually going to move through the system to equilibrate both of the two plates. So what's going to drive the current in this case is actually the capacitor, because it wants to equilibrate, wants to get rid of all that charge. So let's look at the discharging case. So for discharging, again, all we're going to do is take our capacitor. So here's my capacitor. This guy's going to start off with some initial amount of charge. So let's say this is the positive side here. Good. Connect that then to a resistor. Beautiful, which has a resistance of R. Now what's going to happen then is what? These positive charges are going to move through and go in this direction, which means our current then is going to move this way. Okay, so it's going to be the direction of my current. Remember, we look at the direction of positive charges moving. So the positive charges will move to equilibrate or get zero amount of charge on both plates. Okay. So again, let's do the same thing we did last time. Let's use Kirchhoff's rules. So in this case, I'm going to start off at here, point A. I'm going to go around my circuit in the same direction as the current, which means first thing I'm going to do is I'm going to go across the capacitor from the negative side to the positive side. So if I go from the negative side to the positive side, is that positive or negative? That's a positive, right? So in this case, I'm going to get a Q over C. And then here I have my current flowing in this direction. So I'm going to get a minus I times R is then equal to 0. So in this case, we're basically going to do exactly the same thing. So now I'm going to replace that I is then equal to dq dt. But what's the difference here now? So it's not directly dq dt because what's happening to the current? Is the current going to increase or decrease or what? So initially the current is going to be moving, right? But now what's happening is what? The charge is getting smaller while the current is going to remain positive, which means if the charge is getting smaller, this derivative then is going to be negative. Is okay with that? So in this case, the current is actually going to be equal to negative dq dt. Okay, so plugging that in, what we're going to get is a Q over C plus a R times then dq dt is equal to 0. Everyone's doing okay? So in this case, let's subtract this term over here. So I'm going to get a R dq dt is equal to a minus Q over C. Just like last time, we want to bring all the t terms to one side, all the q terms to the other side. So in this case, we're going to get a dq over q is equal to a minus dt over rc. Okay with that? Same thing, we're going to integrate, but this time I'm going to integrate from some initial amount of charge to a final amount of charge. Let's call that q initial to some final charge of q. And this time I'm going to integrate from 0 to t. What's the integral of 1 over q dq? Natural log, so it's going to be the same thing then as the natural log of q over q initial. And that's going to be equal then to a negative t over rc. Again, what I want is q. So how do I get rid of natural log term? Exponential, right? So now I'm going to get a q over q0 is equal to an e to the minus t over rc. Or finally, the charge as a function of time is equal to the initial charge e to the minus t over rc. Okay, what's that? Oh, it's because the charge is getting smaller over time, which means the derivative would be negative, right? Because it's getting smaller over time. Just like if something is approaching, say, so let's say here's my origin. If something is approaching my origin in this direction, so let's think of position, for example. My position is getting smaller, which means in this case, my velocity would be negative because I'm approaching the equilibrium position. Okay, so that derivative would be negative. But we know our current is moving, which means our current is always moving in the same direction. So our current is going to remain positive the entire time.
And what's causing that current?
So the current is moving because the charges are going to keep moving until both sides become 0 amount of charge. That kind of makes sense. So since my current is always moving in the same direction, the current would be positive while the derivative of the charge would be negative. Okay, so I have to insert this extra negative sign in there to make sure that my current is positive. Because current is always a positive number, right? Because it's a scalar quantity. Okay. What's up, Gideon?
Sorry.
You're fine.
Well, let's so we go back from the negative.
Technically, it goes from the negative to positive. Remember, using our convention is that positive charge moves, not negative charges. In reality, of course, it's negative charges which are moving, so it would actually go in the opposite direction.
Why do you think delay involvement with the convention?
It's just what they've been doing for what?
Since Ben Franklin.
Right. So you're talking what, at least 200 plus years,
But
right?
it's just confusing.
I know it's confusing. Well, I mean, it took us until what, around early 1900s ish before we actually figured out it was actually negative charges moving. And next exam, we'll actually talk about how we know it's negative charges, and that's what's called the Hall effect. But we have to talk about magnetism first. So yeah, so like what, 250 years ago ish is when Benjamin Franklin decided it was positive charges moving. And then it was what, like 200 years later, we finally determined it was negative charges. By that time, people were stuck in their ways, right? And they didn't really want to change.
So now they're just giving us what this is.
Exactly. That's pretty much about it. Exactly. So good. So this is then my charge as a function of time. So now for the discharging, again, let's plot this guy. So my charge as a function of time, again, what's going to happen is that t is equal to 0. This term is going to be 1. So this thing is going to start off at whatever amount of charge this thing originally had, q0, which may or may not be the maximum amount of charge. And then as t goes to equal to 0, or as t goes to infinity, I should say, this thing goes to 0, which means, again, this thing is going to exponentially decrease, asymptoting to 0. Define the current as a function of time. All we're going to use now is this definition here. So I take the derivative of this, I'm going to get what? Simply Q0 over RC with a negative sign. This negative sign kills off that, which means my current as a function of time will simply be equal to what? Q over RC times e to the minus t over RC. This guy here, we're just simply going to define as what? My initial amount of current. So it's going to be my initial current, e to the minus t over RC. So for this guy, we plot this guy as a function of time. And here's t. Here is my current. This thing is going to start off with whatever its initial amount of current is. And then again, exponentially decrease, asymptoting towards 0. So for the discharging case, again, all I really want you to know is this and this. Now notice that tau here is actually the same. So again, we can define tau, or tau is our time constant, which is simply equal to RC again. So this is our time constant. Now, I don't know how many people looked at the extra credits. The extra credit is actually this, but there's a caveat, which is that now the capacitor and the resistor, when it's charging, are not connected in series anymore. They're connected in parallel. Slightly different. So in that case, do exactly like what we did here. Do Kirchhoff's rules with the sign conventions. In that case, there's going to be a junction, so you have to use the junction rule as well. Okay, so you have two loops. Use the loop rule on both of those two loops, and then use your junction rule. And then basically, you're going to kind of repeat what it is I did here. Separation of variables and all that kind of good stuff. So, was doing okay? So that's it. So let's do a couple examples of this, and then we'll finally be done. And then I'll talk a little bit about the group assignments. And then tomorrow, we'll start off with a review. And then after that's review, I'll give you the rest of the time to work on your group assignments. So first one I have this is we have a charging RC circuit, which has a resistor, which has resistance of 20 kilo ohms, has a capacitor, which has a capacitance of 0.3 microfarads, and it's connected to a battery where the EMF here is equal to 12 volts, or you just want to call it V is equal to 12 volts, whatever you want to do is fine. So we want to find a whole bunch of slew of things. First thing is we want to know what's the time constant. So let's start off with the time constant. We know that's tau, so that's simply R times C. So in this case, our time constant is going to be R times C. And we know R, again, is 20 kilo ohms. And we know C is 0.3 microfarads. So using our unit conversion, so that has to be in ohms and that has to be in farads. So that's 20,000 times 0.3 times 10 to the minus 6. And this has units of seconds because it's a time constant. Multiply all that out, that then works out to be, according to this, 3.6 micro. I multiply things out correctly. What are we finding? Just the time constant. Good question. So we have microfarads. Let's see. Did I break down? Oh yeah, 6 milliseconds. Okay, I was looking at the wrong one. Thank you, Jamie. Yeah, that didn't look right to me either, but that's fine. So 6 milliseconds, which of course is 6 times 10 to the minus 3 seconds. There we go. Yeah, looking at the wrong line. It's okay. Okay. So next up, we have to determine the maximum amount of charge on the capacitor. So we already said that the maximum charge is equal to when the current is equal to 0, which is dictated by simply the battery. So the maximum charge is equal to the EMF in this case, or the potential of the battery times the capacitance, where again, we know the EMF in this case is simply 12 volts. So it's going to be 12 times 0.3. I'm just going to write this as microfarads. So microfarads, which is now 3.6 microcoulombs. Good. Read the right line. We're doing okay. Part C then simply says the time it takes to reach 99% of the charge. So what we want to know, or what we want, is that what? Q is equal to 0.99 times Q max. So we're saying that the total charge on this thing is equal to 99% or 0.99 times Q max. Okay. We also know this is going to be 0.99 times Q max, which is simply E times C. Now we know the charge as a function of time for a charging circuit is equal to C times E times 1 minus E to the minus T over tau, where tau again is our time constant. So basically, all we have to do now is solve this thing now for the time. Nice and easy. What's up? Yes.
So that's E times C or B times C?
Yes, correct.
Sorry. Oh, no.
Okay. You're fine. So good. So in this case, CEs are going to cancel. We don't care what the maximum charge is, right? So we're going to be left with then 1 minus E to the minus T over tau is equal to 0.99. We want the T, so I'm going to add this term over here, subtract this term over here. So I'm going to get a 1 minus 0.99, but what's 1 minus 0.99? 0.01, good, is then equal to E to the minus T over tau. Now we have this negative sign here, so I'm just going to invert both sides to make this guy now a positive. Of course, I don't have to, but I'm going to go ahead and do that anyway. So inverting both sides, I'm going to get an E to the T over tau is then equal to a 1 over 0.01. But 0.01 is the same thing as what? 1 over 100, right? So I get a 1 over 100, but what's 1 over 100? 100. So it's going to be simply 100. How do I get rid of an exponential? Natural log, so let's do that. So finally, I'm going to get T over tau is equal to the natural log of 100, or finally, T then is equal to tau times the natural log of 100. Tau we already know, that is our 6 milliseconds. So I'm just going to leave this at 6 milliseconds multiplied by the natural log of 100. And it says that this thing is going to take 28 milliseconds for this thing to reach 99% of its maximum charge. Okay. Now, if I wanted it to reach 99.9%, then the difference is now this would be 1,000. Then I'd have natural log of 1,000. And if I wanted to reach 99.99% of the maximum charge, that would be 10,000 instead. Okay. Now, again, theoretically, this thing will not reach maximum charge until T goes to infinity. Okay. Next up, what we want to know then is what is about maximum current? So the maximum current, or part, what is this, D, we know the current maximum is when the charge first starts to move, which means there's zero capacitance, which means it's only dictated by the battery. So my maximum charge is simply the EMF divided by the resistance. So it's going to be 12 volts divided by 20,000 ohms, which according to this works out to be 600 microamps. Nice and easy. Not too bad. Nice. So one more. And that finally says, when I find it, should be this one. So it says a turn signal flashes twice a second. So I know we live in Evansville. Nobody uses their turn signal. So turn signal is the thing on the side of the car which flashes. Okay. So great. So that thing flashes 2 times a second. So that the time constant is 0.5 seconds. Okay? So it says the RC circuit, which is controlling this, may have a capacitance of 1 microfarad. And it wants us to estimate or just determine what is the resistance of the resistor. I've been talking about this stuff in a little bit. But this is beautifully easy. So what do we know? We know the time constant tau is simply R times C. In this case, we know tau. We know C. How would we get R? Just divide by C, exactly. So R then is going to be the time constant divided by C, which means that this is going to be equal to, what was the time constant? 0.5. So 0.5 seconds divided by the C, which is 1 microfarad. So that's 1 times 10 to the minus 6. So this thing is then equal to, according to that, 500 kilo ohms. That's it. Nice and easy. As simple as possible. So one thing I want to quickly point out here, anything that happens in a rhythmic fashion is an RC circuit. So again, your blinkers, right? Your turn signal, your window wipers, right? Your windshield wipers. When you're driving down the road and you see those cones that are flashing, those are RC circuits. A pacemaker, if somebody has a pacemaker, make sure that their heart pumps on a regular basis, is an RC circuit. So basically anything that happens on a rhythmic fashion is an RC circuit. So the way that they actually work is that, if I'm charging up the capacitor, connected then to a resistor, what happens in this case then is you're going to reach a maximum charge. But that maximum charge causes the potential here to exceed the potential breakdown, which means that it is going to discharge, which means that you're going to strip charges then from the negative plate to the positive plate, causing this thing to go to 0 charge, so that it becomes completely discharged. And then you're going to do it again, right? So basically in those cones that you see with the flashes on there, it's the gas becomes ionized, right? So when it reaches its maximum amount of charge, it exceeds the breakdown potential of the gas, causing the gas to ionize, which causes it to flash. Now, since it is completely discharged, it then goes through again, reaches maximum charge, exceeds the breakdown, and then flashes again. Right? The rate at which it is flashing is dictated by both the capacitor and the resistor. Right? So if I want it to flash faster, you use a smaller resistor. Right? If you want it to flash longer, or at least longer durations of time, in that case, you would use a bigger resistor. Right? So it just depends on what it is that you want to do. But again, anything that flashes or goes on a rhythmic fashion is simply a resistor. So again, if you look at your windshield wipers, when they go very slow versus when they're going fast, you're just using different resistors. Right? So you're just changing it from one resistance to another resistance, typically with the same capacitance. That's it. Beautiful. We're finally done. We've done everything for exam number 3. So beautiful. So let's talk about our group of comments that I've been ignoring up to this point. But they've all been posted onto what was that, Blackboard since the beginning here. But let's talk about each one of these. So let's talk about this one first. So this one is you have a potential difference across a wire, which then has a voltage of 1.2 volts and has 33 millimeter length, and it has a 18 gauge wire, which means the diameter is 0.04 inches. So from here, you want to calculate a whole slew of different things. So the current, the magnitude of the current density, the drift velocity, the magnitude of the electric field within the wire, which is just going to be the potential divided by the length. So nice and easy. And then the rate at which the thermal energy will appear. So that's just the power. So in this case, you're just calculating the power. These are the constants that you need. So the resistivity of copper is this, and then the number density of copper is that. That's a nice easy one. Just applying all the things that we have learned. One thing I will point out is this will be very similar to one of the exam questions. I'm going to ask something very similar to this, where I'm going to have a particular type of geometry, and then I'm going to ask you basically all these things. What's the drift velocity? What's the current density? How much current do you have? And et cetera. Okay. So it'll be very similar to one of the exam questions. This one is basically just playing with the definition of currents. So this just says you have a steady beam of alpha particles, which have a charge of 2 times the charge of an electron, traveling with a constant kinetic energy of 20 MeV. So first thing we have to talk about is what is an MeV? So MeV is another unit of energy. So an EV is equal to a unit of energy. So first of all, what is an EV? So the EV is the amount of energy you need to accelerate a charged particle through a 1 volt potential. So if this is a 1 volt potential difference, then it's the amount of energy you need to move this charged particle through this 1 volt. This is what an EV means. Now, the way that this translates to joules is E is literally E. 1.602 times 10 to the minus 19. This is a 1 volt potential, which means that an EV is the same thing as 1.602 times 10 to the minus 19 coulombs times 1 volt, which is the same thing as 1.602 times 10 to the minus 19 joules. So the relationship between an EV and a joule is by the charge of an electron, which is 1.602 times 10 to the minus 19. So that's an EV. So here you have a mega EV, and a mega EV is 10 to the 6th. Okay. So this thing carries a current of 0.26 microamps. So what it says is if I have a beam that is directed perpendicular to a flat surface, how many alpha particles strike the surface in 3 seconds? So let's kind of draw what this thing says. So here's my flat surface. All right. And we have a beam of alpha particles coming in. So let's say here's my beam of alpha particles. All right. So these are going to hit, and then they're going to embed themselves onto this flat surface. And basically what it wants to know then is how many alpha particles are on this flat sheet in the time frame delta t is equal to 3 seconds. This is basically what it wants you to find out. Now for this one, what we know is that current is equal to the change in charge divided by the change in time. But since each alpha particle has exactly the same amount of charge, this is going to be the same thing then as the number of alpha particles times the charge of the alpha particle, which is 2 times E, divided by the change in time. So simply solve for the number of particles. That's it. Right. Part B, you have to be a little more inventive because part B is now saying how many alpha particles are there in a length of the beam, which is 20 centimeters long. So all that means then is if I look at this beam and I take a section of this here, which is 20 centimeters long, so this is my L, how many alpha particles are contained inside of here? Okay. The way you're going to do this is you're going to rewrite delta t in terms of the length and the velocity, because the second kinematic equation tells us that the length is simply equal to the velocity times the change in time, which means my change in time then is going to be equal to the length divided by the velocity. The velocity you can get from the kinetic energy. So look at the definition of kinetic energy, 1/2 mv squared, and then you can find the velocity that way. Okay. From there, again, all you're going to do is solve for n. Part C is what we did last exam, which is conservation of energy. So you have the change in kinetic plus the change in potential has to be equal to 0. Use that to find the potential. Nice and easy. Nice, okay. So those are the first two. So let's move on. Current density, that's one we just talked about. What's next? Is this what I want? Close. There we go. So next one is the Kirchhoff's loop rule problems. The only thing I will tell you is there'll definitely be another one like this on the next exam. What's up? Yep.
Some negative value, but
depending on how you define your circuits. Yes.
The amps from the absolute value.
Correct. Exactly. So these are just the absolute value, but yes, you'll get positive or negatives depending on how you define your current directions. Exactly. So these are just the absolute value, and you have to decide basically the direction. Exactly.
Because I got that last night, and I was like, what?
Oh, with negative signs? Yeah, it just depends on how you take, for example, the currents are here, they're going this way, or they're going this way, and et cetera. So yeah, so you just have this guy, you know now the resistances of the four resistors. You also know the battery potentials for each one of these batteries. So this one and this one. And all you're looking for is the current going through each one of these resistors. Now, one thing to point out here, and this is a mistake I've seen a lot in previous exams, if I ask you the current moving through all the resistors, and here there are two resistors in series with each other, just because there's a different resistor doesn't mean there's a different current. So here, because there's four resistors, does not mean there are four different currents. There are only three different currents because there are only three different legs of the circuit, right? So from here all the way through here is one current. From here to here is another current. From here to here is another current. So don't say there's one current through here and a different current from here, because why is that not true? Because they're in series with each other. The current has to be the same. So just because I ask you what is the current through each one doesn't mean they have to have different currents. Okay with that? So that's the first one. Again, this will be something very similar to what you're going to see on the exam. Then there's the second Kirchhoff's problem, which is this one. Again, just more practice. So notice here you have three batteries all pushing current in the same direction. But what's up? Sure. There's two what? Yes, because it's a total of three loops, but there's going to be two independent ones. Yes, which is what you're going to see on the exam. So I'll give you a three loop system, but only two of them will be independent. I'm not going to go bigger than that. Homework, maybe, but not here. Not on the exam. I don't want you to spend 26 hours just writing everything down because, you know, we don't have that much time. So one thing to point out here is all three of these batteries are all trying to push currents into the same direction, but we know by the junction rule, not all the currents can be entering here. One current has to be leaving, which means that one of these batteries are going to have currents forced in the opposite direction, which means one of these batteries is going to be charged. The other two will be being discharged. Now, the way you can determine which one is probably going to be charged is by the size of the EMF, which means the one that has the lowest EMF is going to be the one that is being charged, because the other two are going to overpower it and force current to go into it, which means these two should be discharging and this one should be charging, which means the current is going to move in this direction. Now, in a problem, I could ask you which one of these batteries is being charged. The way you know if it's being charged or not is the direction of the current. If the current is moving away from the battery, it is being discharged. If it is moving towards the battery, it is being charged. Okay with that? What's that? Yes. It wasn't in the folder? Okay, I'll make sure it shows up on there. Gotcha. Okay. All I can say is I can't be perfect all the time, so it's great. But it's okay. Let's talk about this one real quick. So this is a continuous charge distribution one. So this actually was one that should have shown up on the previous exam, but we didn't get that far, so we're going to do it here. So all this is asking is what is the potential at this point from a continuous charge distribution, which means that you're doing the integral. The potential is equal to K times the integral of dq over R. So this one, because it's a bent object, you turn it into an arc length, which means that your small little dq here has a length of dl, where dl is going to be r d theta. Okay, so anytime you have a bent thing like this that's not filled in here, just use arc length. Right, so you're just doing this for any random angle speed. So it's symmetric on both sides. So that means I have half a phi on this side and half a phi on this side. Exactly. So that's my continuous one. And then I have another one here, which is conservation of energy and a constant, or let's see, discrete particles. So the first one is just conservation of energy, saying that you have two electrons fixed some distance apart. And I'm going to take a third electron and shoot it so it has enough energy to make it at the midway point between the two. So all you're looking for in this case is what is its initial speed for it to stop exactly at that location. What's that? Yep. Yep.
The biopotential energy is going to be equal to 2 times like the distance from like it's the electric field of
Right.
the electron times the distance times the charge multiplied by 2 because two electrons on each.
Well, not the electric field, but potential. Yeah, the electric potential.
Well, I was saying that like the electric potential distance, the electric potential is equal to the electric field times the distance. Good.
Well, it's not. So it's the integral of the electric field over the distance. So not just multiplied by the distance, especially when the electric field is non-constant.
Okay.
So the only time we multiply by the distance would be if the electric field is constant, but here it's not constant because it's a point charge.
Oh, I'm saying, because, okay, so I have a quick question.
Sure.
In this case, because, we're taking the initial versus final to find the total.
Right, but the initial potential of that original electron infinitely far away is just zero.
Yes, it's zero. Right. The second part.
Right, so the second part, what you're looking for is you have one electron here, you have another electron here, and you're looking at the midway points, which means you just care about half the distance here. This is half the distance here. So your total potential is then going to be equal to the potential of the first electron plus the potential of the second electron. But since they're equal distance away with same charges, this is then just going to be twice the potential of one of those electrons. Is that what you mean? Yeah, so this is just going to be what? K E over D over 2. Right.
That's what I was asking.
Okay. Okay, sure, fine. You like to do that to me, but it's fine. So, and then this one is find the potential at point P from just charges. Now, one thing to point out is when it comes to potentials versus that of electric fields, with electric fields, this charge would cancel this charge, and this charge would cancel this charge because we have the directional components, right? Which means this one would cause an electric field going this way, and this one causes an electric field going this way, which means the net electric field between those two is zero, right? But that's no longer the case because remember, with potentials, I don't care about directions. All I care about is the value of the charge, which means at this point here, I'm going to double up the potential because I have two equal amounts of potential. Now, the only way to cancel potential is if they come with opposite signs of the charges. So this potential is going to cancel with this potential, but that's it. Now, when it comes to the electric field, though, these would cancel, but these would no longer cancel because the total electric field from this guy would point this way. Electric field from that would point that way. So the total electric field would only point towards negative Q3. Okay. So just note that is different. Is that the last one?
Yeah.
Nope, we got two more. So might have to finish talking about these tomorrow. But this one is another one, again, very similar to what we might see on the exam. So this says you have a resistor, which is the light bulb. This gives you the resistivity. It gives you the radius. It gives you the resistance. And the first part wants you to find the length. So you just use the definition of resistance from resistivity. It says your potential difference across it. So in this case, you're looking for the magnitude of the electric field, which again is just going to be the potential divided by the length that you find in the first part. Here, the number of electrons per second is actually the current per charge. So you're going to find the current and divide that by the charge of the electron because that's equal to the number of electrons per second. Power dissipated, of course, is the same. And then the last part here is how much are they going to charge you if you leave it on for a month? Okay. So notice this is a kilowatt hours. This is a unit of energy, not power. Remember, power is what? Energy per time. You're multiplying by time, so that's going to be a unit of energy. Right? So the way that they actually charge you from the electric company is they charge you by kilowatt hour, which is the amount of energy that you're actually using in that particular time frame. Mm-hmm. So here they're saying they're charging you 15 cents. So this hour here, all you have to do is take your power from the previous part and multiply by the amount of hours there are in 30 days. Okay, multiply that by 0.15. That's going to be the amount of money that you have, which will be about $8. So in theory, you would only pay $8 to have that thing go on for a month. But in reality, of course, they're going to charge you hookup fees. They're going to charge you delivery fees. They're going to charge you every other fee that they could possibly can. So that $8 turns into like 150. Right. We'll talk about the last one tomorrow after we do the review. And life will be great. And I'll put up that last one on there. You said the one Kirchhoff Looper one. I know. I'm saying I'll put that on the blackboard.
Oh, you're saying.
Yeah. No. The last one we just have one more, which is I forget what it is, but it's fine. It's fine. It's up there. So great. Yeah.
I did like a little bit